Just imagine the gap between today's roughly 250 watt-hours per kilogram and a theoretical 12,000 watt-hours per kilogram. That difference could represent one of the biggest revolutions in battery technology ever seen. The electronics and electric vehicle industries are still largely dependent on batteries that deliver around 250 to 270 watt-hours per kilogram. But CATL is exploring lithium-air battery technology with a theoretical energy density approaching 12,000 watt-hours per kilogram, a figure remarkably close to the energy density of gasoline. If even a fraction of that potential can be achieved commercially, electric vehicles could eventually travel more than 1,600 kilometers on a single charge. Such a breakthrough could seriously challenge the century-long dominance of internal combustion engines. Unlike conventional lithium-ion batteries, which depend on materials such as nickel, cobalt, and manganese, lithium-air batteries use a fundamentally different approach. Instead of storing all of the reacting material inside the battery, the system draws oxygen directly from the surrounding air. That is why lithium-air batteries are sometimes described as breathing batteries. The basic idea is surprisingly simple. Current battery packs contain a large amount of material that either stores energy, supports the structure, or participates in the chemical reaction. Lithium-air technology can potentially reduce the amount of active material that needs to be carried inside the battery, dramatically increasing energy density. The theoretical numbers are extraordinary. Lithium-air batteries could potentially reach around 12,000 watt-hours per kilogram, approaching the roughly 13,000 watt-hours per kilogram energy content associated with gasoline. That is the kind of figure the battery industry has been chasing for decades. For comparison, modern lithium-ion batteries used in electric vehicles generally deliver around 250 to 270 watt-hours per kilogram. Solid-state batteries, often considered the next major step in battery development, are targeting roughly 500 watt-hours per kilogram. Meanwhile, laboratory lithium-air prototypes have already exceeded 1,200 watt-hours per kilogram in experimental conditions. Even that experimental figure is more than 4 times the energy density of many current commercial batteries and considerably higher than the targets associated with conventional solid-state technology. If lithium-air batteries can eventually be commercialized, the transportation industry could be transformed. Researchers believe vehicles using this technology could potentially achieve ranges exceeding 1,600 kilometers per charge. At that point, one of the biggest objections to electric vehicles, range anxiety, could become far less important. And the impact would not stop with passenger cars. Long-haul electric trucks, autonomous taxis, electric aircraft, and large-scale energy storage systems could all benefit enormously from much higher energy density. But there is a major reason lithium-air batteries have remained largely confined to research laboratories. The technology has faced serious technical problems for decades. Moisture, carbon dioxide in the atmosphere, catalyst degradation, limited cycle life, safety, and overall stability have all made commercial production extremely difficult. These challenges have kept lithium-air technology from becoming a mainstream battery solution since researchers began seriously investigating the concept decades ago. However, recent developments suggest that progress is accelerating. In 2024, researchers from the University of Illinois Chicago, Argonne National Laboratory, and California State University, Northridge demonstrated a lithium-air battery capable of operating for more than 700 cycles under air-like conditions. Then, in 2025, researchers at Argonne and the Illinois Institute of Technology announced a prototype capable of approximately 1,200 watt-hours per kilogram, while approaching 1,000 charge cycles at room temperature. That represents an important improvement for a technology that has historically struggled with durability. It also creates the possibility that lithium-air batteries could eventually move toward commercial applications after 2030, although significant engineering challenges still remain. CATL's interest in lithium-air technology also reveals a broader long-term battery strategy. In the short term, the company continues developing lower-cost sodium-ion batteries aimed at mass-market applications. CATL introduced sodium-ion technology several years ago and has worked with automakers to integrate the chemistry into different vehicle platforms. In the medium term, solid-state batteries could provide improved performance and charging characteristics. But over the longer term, lithium-air technology represents something much more ambitious: an attempt to push energy storage beyond the limits of conventional battery chemistry. What makes this particularly significant is the company pursuing it. CATL is not a small startup experimenting with an unproven idea. It is one of the world's largest battery manufacturers and a dominant supplier to the electric vehicle industry. When a company operating at that scale invests serious research effort into lithium-air technology, the rest of the industry has a reason to pay attention. The technology may still be years away from widespread commercial use, but for the first time in decades, researchers are exploring a battery concept with theoretical energy density approaching the energy content of fossil fuels. If CATL succeeds, lithium-air would not simply represent another battery upgrade. It could fundamentally change the competition between electric vehicles and gasoline-powered vehicles. And the implications become even more interesting when we consider how this technology could affect Tesla's future vehicles. Most discussions about lithium-air batteries focus on increasing driving range. But the real impact could be much larger. A dramatic increase in energy density could change which electric vehicles are practical, profitable, and scalable. One of the biggest potential beneficiaries would be Tesla Semi. Among Tesla's vehicles, the Semi could gain some of the greatest advantages from a major improvement in battery energy density. The problem facing long-haul electric trucks is straightforward: batteries are heavy. Analysts have estimated that a Tesla Semi may require a battery pack approaching 1 megawatt-hour to deliver its targeted long-distance range. That enormous battery can provide impressive performance, but it also adds substantial weight and cost. Now imagine a lithium-air battery capable of even 1,200 watt-hours per kilogram, still dramatically below the theoretical 12,000 watt-hour target. Even at that much lower figure, the amount of battery mass required for the same amount of stored energy could fall significantly. Instead of carrying several tons of battery material, a future electric truck could potentially achieve similar range with a much lighter pack. The weight saved could then be converted into additional cargo capacity. For trucking companies, that could have direct financial value. This is why lithium-air technology could ultimately be even more disruptive for trucking than for passenger cars. Fleet operators are not primarily concerned with acceleration or top speed. Their priorities are payload capacity, operating expenses, uptime, and profitability. A lighter battery could improve all four. More importantly, lithium-air technology could remove one of the remaining advantages diesel trucks have over electric trucks. Imagine a future Tesla Semi capable of traveling 1,500 to 2,000 kilometers between charging stops. That could completely change long-distance freight operations. Routes that are difficult or uneconomical for electric trucks today could suddenly become realistic. Another major potential beneficiary is Tesla's Robotaxi network. Elon Musk has repeatedly emphasized that autonomous transportation economics depend heavily on vehicle utilization. Every minute a robotaxi spends charging is a minute it is not carrying passengers and generating revenue. Current electric vehicles already offer impressive efficiency, but a future lithium-air battery could take utilization to another level. Imagine a cybercab operating throughout the day and traveling more than 1,000 kilometers before needing to recharge. Charging downtime could be dramatically reduced. Fleet operators could transport more passengers using fewer vehicles, increasing revenue per vehicle while potentially reducing infrastructure requirements. For Tesla, this could be extremely important because autonomous transportation is expected to become a major part of the company's long-term business strategy. A vehicle that can remain in operation longer while carrying a lighter battery could improve the economics of the entire Robotaxi network. Cybertruck could also benefit significantly. Pickup trucks have a unique problem because customers expect both long range and strong towing capability. The moment a heavy trailer is attached, energy consumption increases dramatically, and driving range can fall sharply. Lithium-air technology could potentially solve this problem in two different ways. Tesla could keep approximately the same battery weight while dramatically increasing towing range, or it could reduce the battery size while maintaining similar performance. Either option would make electric pickups significantly more competitive against gasoline and diesel trucks. For customers towing boats, campers, trailers, or construction equipment, that could be a major improvement. Range anxiety becomes much more serious when the vehicle is carrying a heavy load. A much higher energy density battery could significantly reduce that concern. There is another category that could benefit as well: future autonomous mobility vehicles. If Tesla eventually develops larger autonomous shuttles, delivery vehicles, or commercial transportation platforms, battery energy density will become increasingly important. Vehicles designed to operate almost continuously throughout the day gain enormous value from every kilogram of weight saved and every additional kilometer of range. This means lithium-air batteries could potentially enable entirely new business models rather than simply improving today's electric vehicles. However, Model 3 and Model Y may not be the first Tesla vehicles to receive this technology. That might seem surprising because these are Tesla's highest volume products, but breakthrough battery technologies typically enter the market through premium, specialized, or commercial applications before reaching mass-market vehicles. The main reason is cost. Early lithium-air batteries are likely to be extremely expensive. Manufacturing complexity, limited production volumes, and unresolved engineering challenges could make the first generation much more expensive than conventional lithium-ion batteries. Tesla's mass-market vehicles depend heavily on low costs and highly efficient production. Putting an expensive experimental battery into these vehicles too early could undermine their affordability. Instead, Tesla could continue using improved lithium-ion and LFP batteries while eventually moving toward solid-state technology as those systems mature. Lithium-air could then be introduced once the technology becomes reliable and economical enough for large-scale production. The Roadster presents a much more interesting possibility. Because it is a premium, low-volume, performance-focused vehicle, the Roadster could potentially become an early platform for an advanced battery technology. A future Roadster using lithium-air cells could theoretically combine extremely long range with extraordinary acceleration. That kind of vehicle would serve as a technological showcase, demonstrating what next-generation energy storage could achieve. However, even if the Roadster receives such a battery, its overall economic impact would probably be smaller than the impact on Tesla Semi or an autonomous taxi fleet. The Roadster would primarily demonstrate the technology rather than completely transform Tesla's business model. Perhaps the most exciting possibility exists outside Tesla's current vehicle lineup. For decades, electric aviation has been limited by one fundamental problem: batteries simply do not contain enough energy per kilogram. Adding more batteries increases weight, which then requires even more energy to fly. It becomes a difficult cycle. Lithium-air technology is one of the few battery concepts with theoretical energy density high enough to potentially change that equation. If Tesla ever enters electric aircraft or electric aviation, a breakthrough chemistry such as lithium-air could become essential. The same technology that could transform long-distance trucking could potentially unlock entirely new forms of electric transportation. But all of these possibilities depend on one enormous assumption. Lithium-air batteries must move from laboratory demonstrations into reliable, mass-produced products. That remains the industry's biggest challenge. Despite prototypes reaching hundreds of cycles and energy densities above 1,200 watt-hours per kilogram, major problems still need to be solved. Moisture sensitivity, carbon dioxide contamination, cycle life, manufacturing scalability, safety, reliability, and cost all remain critical obstacles. Until these issues are resolved, the theoretical 12,000 watt-hours per kilogram figure remains exactly that, a theoretical target rather than something consumers can buy today. Nevertheless, CATL's research direction is important because it provides a glimpse into where one of the world's most influential battery companies believes energy storage could eventually go. This is not simply about making today's batteries slightly better. It is about pursuing a technology that could fundamentally redefine the limits of electric transportation. If lithium-air batteries eventually become commercially viable, Tesla Semi could become one of the biggest winners. Robotaxis could become significantly more profitable. Cybertruck could overcome one of its biggest limitations. The next generation Roadster could achieve performance and range that seem impossible today. And entirely new categories of electric transportation, potentially including electric aircraft, could become realistic. For decades, battery technology has been the biggest limitation on electric mobility. Lithium-air represents one possible path toward breaking through that limitation. If CATL and other researchers can turn the technology's theoretical potential into a reliable commercial battery, the debate around electric vehicles could change completely. The question may no longer be whether electric vehicles can compete with gasoline-powered vehicles. Instead, the question could become whether gasoline-powered vehicles can keep up with electric ones. What do you think? Could lithium-air batteries really become the breakthrough that finally eliminates range anxiety and transforms electric transportation? Let us know your thoughts in the comments. If you enjoyed this video, make sure to subscribe to the channel for more updates on Tesla, electric vehicles, batteries, and the technologies shaping the future. Thanks for watching, and I'll see you in the next episode.